He's back. All right. Welcome, everybody, to the Utah Go user group. We took a month off because it was on the 4th of July last time, but Nathaniel's worth the wait. So like always, to all our presenters, we give a little, we'll call it a care package. It has a t-shirt. So we're going to do a new t-shirt design every year. This is this year's. I took a lot of crap for putting that on the back, but whatever. So this is the t-shirt. Yes, there's text on the back. Sorry, you don't have to wear it in public. And then this is the coveted piece of this. When you present, you get the Utah Go presenter pin. This is these are locked up in the back. You can't get these unless you present.
Is there an armed guard?
So, yeah, armed guard, security system, whole 9 yards. So don't even try. Anyway, we're welcoming Nathaniel. Thank you for presenting. It's been a while since, I don't know, it's been over a year. Yeah, 2 years maybe.
2 years probably, yeah.
Yep. Anyway, welcome Nathaniel. Let's give him a round of applause.
Well, I'm excited to be here. Today we'll be talking about building DSLs with Go, and I'll talk about what a DSL is in a second. But first, I want this to be super interactive. This is a meetup. We're here. We're chatting. If you got a question, just interrupt me. Raise your hand. We'll just chat. I've got a ton of content to cover, so we don't cover it all. That's fine. If we want to go down like some rabbit hole, let's go down some rabbit hole. It'll be fun, and we can learn all kinds of things while we're at it. And if we just want to just plow through it really fast, we can do that too. Whatever you guys want. This is for you. It was fun for me to put together and to think about and learn. But I want this to be just as much interaction and learning for everyone as possible. So, building a DSL. So a DSL is a domain-specific language. And, well, what is a domain-specific language? I'm going to be a little bit redundant here. It's a language built for a specific domain. And, but when you say domain, you mean like problem, right? So, a couple of examples for the domain-specific language are like Go templating. I don't know if you've seen like in Go, you can do templating language. You get the little curly brackets and then everything else. That little curly brackets and everything that happens inside of there is the domain-specific language. Or a bunch of other examples, and we'll come to some of them in a second. But there's two different kinds of DSLs when you talk about them, and people are very clear about which DSL they're talking about when they talk about DSLs. So the two different kinds are the internal versus the external DSL. So an internal DSL is a language that is like a subset of another general purpose language. For example, lots of people use Ruby to write internal DSLs because Ruby is a very, very flexible syntax, and so they'll take some very small subset of Ruby and they'll say, this is our DSL, and you're actually writing real Ruby code, but they've changed it so much that it doesn't actually look like Ruby code anymore. But it's around this specific domain that they're trying to do. They've written classes and things to support that, and so that's an internal DSL. We're not talking about internal DSLs today. We're talking about external DSLs. External DSLs their host language, there's nothing really, there isn't a host language, really. This means that we just get a text file that is the language, and we have to parse it and understand what that language means and what it does. And it's not part of any existing lexer or parser of another language. So we're talking about external DSLs today. And then a domain-specific language, again, it's about a specific domain. So these typically are not general-purpose languages. They can't do general-purpose Turing-complete computations. That's not their purpose. Their purpose is to do work in a specific domain. And we'll go through a couple of examples of those domains. Okay, so why create a DSL? It's fun. Let's be honest here. It's lots of fun. Okay, so another reason is it enables you to create a language in which create the correct abstractions for the domain you're trying to solve. So, I mean, think about English for a second, like not programming languages, so like fluent speaking languages. The way we talk really influences the way we communicate, and the way we're able to communicate ideas and to communicate. And so if you could control the language in which somebody spoke, you could really control the ideas they're able to communicate. And so you could basically say, don't go over here. I don't want you to talk about those things. I want you to focus on these things. And I want you to talk about these parts of the problem that I care about. And so that's really the point of a DSL. is to constrain what your users are actually thinking about and what they're talking about to point them in the right direction, right? If you want your users to be able to do anything under the sun, don't use a DSL, right? Use a general purpose language, build frameworks and libraries, that kind of thing. If you're trying to build a system where you're trying to point your users in a certain direction and get them to think about a problem in a certain way, that's a great use case for a DSL, okay? And a couple other points, they're easier to learn because they're simple, right? They typically don't have tons and tons of features. They're just specific to a domain. And if you're an expert in that domain, but you're not necessarily an expert in computer science, you could actually pick up the language because it's really familiar in concept to you, even though the concept of programming may not be very familiar to you. So those are some of the reasons why you'd want to create a DSL. So some examples. So I mentioned already Go templates. So like I said, little curly brackets, there's like if expressions in there, range expressions, all kinds of different ways of putting logic into templates so that you can generate a bunch of data, right? And other things are like rules engines. In fact, game engines. A lot of times when people go develop a pretty mainstream game, the gameplay is going to change a lot from their first idea to their final production idea, and they don't want to have to spend so much time rewriting a bunch of code to change just gameplay. So they'll actually write a DSL to describe the elements of their game, and then they'll use that DSL to actually mutate the game as they go along and allow them to quickly iterate on gameplay concepts as opposed to all the classes and frameworks of the actual game itself. Configuration management, who's used Puppet or Chef, right? Like, those are DSLs, right? They're specific languages in the domain of configuration management, where they're declarative because configuration is essentially applying a state, right? And all these properties of the language carry forward to how you think about configuring a machine. And so that's another example. Okay, so then the reason I'm talking about it is TickScript is a domain-specific language that I've written for the product that I write called Capacitor. So the domain of Capacitor is metrics systems. So you've got your metrics data coming from your servers, or coming from your application, or coming from IoT devices, and you want to do something with that data, right? It's just this big stream of data. The primary index on the data is time because it's coming as time progresses. And you want to do things with that data. So this little code block here is an example of what the TickScript DSL looks like. So unless you're familiar with Capacitor before, this may look very foreign to you, but at the same time, hopefully quite familiar. In the sense that if you're familiar with like Unix and piping, you kind of see these pipe characters and they're kind of steps in the processing, right? So the very first thing you do is you select from, and you select certain data, right? And then, okay, so you've got the data that you care about because you're sending a whole bunch of data to your system. So now we've grabbed just the data about the mem, or the memory of the systems, right? And the next thing we're going to do is we're going to window that data. So we've got this stream of data, we're going to window it up, and we're going to break it up every 10 seconds, but each window is going to be a minute long. So we just described overlapping windows, right? Where every window is a minute long, but it's sliding at 10-second intervals, right? And then what are we going to do with each window? Well, we're going to compute the mean of that window. Specifically of the field called used percent, or in other words, the percentage used of the RAM on the box. And because that data from the database mem has that field, that column on it. And so then we've got the mean for every 10-second window, or every minute window every 10 seconds. And then we're going to send it to an alert. And we're going to trigger an alert if that free percentage is greater than 70, or the used, not free, sorry. If the used is greater than 70, 85, or 90, we can control whether it's an info critical or info warn or critical alert. And so that's the point of a DSL. Simple. You may not know the language very much. Maybe you wouldn't be able to write a new one right now, but you can read that and you can follow what it's doing. And you can understand the domain of what's going on. Okay. So today, we're going to talk about a really small DSL that I wrote over the weekend. And it's been fun. In fact, I liked it so much that I'll probably actually use it beyond today, and because I love home automation and like tinkering around in my house. And but it was fun. So here's the DSL, here's the language that we're going to try and write today. I'm not going to go through all the details because all the code actually, by the way, is on GitHub. I have a link at the end. So if you want to like dig into the details, you can. But we're going to cover the highlights of writing a DSL for this language. So I just came up with this language. I was like, what are the kinds of things I want to do in a home automation scenario, right? So maybe I want to set the master bedroom light to 50%, dim it at 50, right? Maybe I want to get the value of the master bedroom light and make the downstairs light that same value, right? Okay, that's one thing I could do. Maybe I could define an entire scene, nighttime, and I turn off all the lights, I lock all the doors, and then I turn the porch light on. So, it kind of looks like we're here or someone's less incentivized to rob the house or something, right? And then I set up this condition: when any of the doors are unlocked, wait 5 minutes and then lock the door, right? So if I leave my house after the nighttime mode has been activated, and then I forget to lock the door, it'll lock it for me, right? Or if I leave it, run a quick errand, take out the trash, whatever, and come back in, and I forget to lock it after I come back in, again, it'll lock it for me, right? So this is really simple, but these are the kinds of things that all the home automation systems are trying to get you to do. But they're trying to get you to do it in a point-click manner, and I'm a coder. I like code, right? I like a nice, simple, declarative syntax to be able to describe these concepts. So this may not be the best home automation language, but it was definitely one, and we're going to try and write a DSL for it, right? And at the very bottom, we set start and stop times for when nighttime mode happens. Okay, so this is what we want our language to look like, and we know what we want it to do, but where do we start? How do we get this to happen? What do we do? Okay, so in executing a DSL, there's basically 3 steps. We first have to lex it, and then we have to parse it, and then we can evaluate. This is actually very simple. You can put in lots of other steps in here if you felt like it, because you needed to abstract different pieces away and not have them tightly so coupled. But at a bare minimum, you need these 3 steps. And they're actually really simple, okay? So what is lexing? Or when we say lex, what are we talking about? Lexical, I don't even know what the word means. Assume it means referring to characters. And that's what a lexer does, is it reads characters at a time from your text file that has your language, and it creates a list of tokens, right? So, for example, we'll get into another example, but the word set, right? The lexer is going to get the letter S, then it's going to get the letter E, then it's going to get the letter T, and it's going to go, oh, I know what that is. That's a set token. And it's going to pass up a set token upstream. And that way, the next person gets to deal with higher order concepts instead of character to character, right? So the lexer's job is to take character at a time and create tokens. Okay. So what's the parser's job? Well, it's to take tokens and create an abstract syntax tree. That's what everybody calls these things when you're defining a language. Essentially, turns out a tree structure is a really good way of representing the syntax of a language. Because think about your calculator for a second. If you have 3 plus 4, right, or reverse Polish notation, 3, 4 plus, doesn't matter, you're going to get a node in your tree that's got the plus on it, and it's going to have a 3 and a 4 connected to it. And so that is your syntax saying, hey, I'm trying to communicate that I'm going to add the numbers 3 and 4. Right, so that's what an abstract syntax tree is. So we need to build a tree out of this list of tokens. So when we see a 3, then we put that on the tree, and then we see a plus, oh, we make that a parent, and we see a 4, make that a child, right? In fact, that's why reverse Polish notation is popular, because it's a lot easier to write a person vector score. Okay, so then after we have an abstract syntax tree, we need to do something with it. That has to have meaning to us. So we need to evaluate it. We need to take that tree, see what it says it's going to do, and then actually go take that action. Okay, so let's dive into lexing and what that's going to do for us here. So lexing, like I said, we consume runes. So who's familiar with a rune in Go? Okay, not seeing a ton of hands. So in C, there's a type called a char, which represents 8 bits or a byte, and that's typically what you would process when you process characters. All ASCII characters take up a single byte, but UTF-8 characters take up more than a single byte because of the coding, right? So Go is really nice. You can actually read files runes at a time that may be multiple bytes wide instead of just 1 byte at a time. And that way, you can actually correctly understand. So this language that we've written is fully UTF-8 compatible. Right? We can write this language in Chinese with the exception of those keywords, and it would still work just fine. Okay. So we talked about tokens, but what is a token? What's our type for a token? The type for a token is right here. We've got a position. This position just stores the line and character information for that token. So where did we find it in the file? Really useful later for lots of things. For example, useful error messages like, hey, I got to this point in the file and I'm really confused. You typed something wrong, right? So you can point the user right at the error. Okay? It's also got a type. So what is this token type? The kinds of types are at the bottom. You typically create two special types. One is an error type, and we'll see why in a second. And then the next is an end of file type, meaning I've reached the end of the file. And then you create a bunch of other types. So we create a token called set, which represents, hey, we found the set keyword. We create a token called get, hey, we found the get keyword, et cetera, right? Other things beyond keywords is like we found a path separator, found a slash, right? Or we found a word. We found a contiguous block of numbers and letters that don't have path separators or other special characters in between it. So we just found a word, right? So that's the kind of things the Lexer is doing. It's just taking in character or room by room and saying, what are these things? Okay? And notice back here that the Lexer does not have an error that it returns. It simply returns a channel of tokens. That's because when the Lexer encounters an error, it just puts the error token on the channel. And the parser will just read that off, see it, and go, oh, error. And then the parser can handle its own error at that point. So it can communicate the error in band instead of out of band. Questions at this point? Okay. So we're going to jump into how the Lexer works. So we've got tokens, and we know we want to read character by character, and we want to produce a list of tokens, but how do we do that? Okay. So this little loop and type definition of a state function comes from a talk from Rob Pike on lexing and parsing and Go. And a lot of this talk actually comes from there. So thank you to him for this great idea. In fact, I used his talk to start writing TickScript when I first did it, because it was a great launch off point for learning how this works. In fact, when he was talking about how he wrote a Lexer and parser for the Go templating engine. So again, I'll have a link to that source, but if you want to go see his code that does lexing and parsing, just go look at the source code for text/template/parse. And it's all in there and it's great. Okay, so back to how this works. So a Lexer needs to produce a list of tokens. But sometimes it can get really complicated to write a really, really big function and say like, okay, I found a set keyword, what's next, right? And then all these conditions and edge cases and state needs to be remembered by the Lexer. It'd be really nice if we could just write this really simple, nice encapsulated piece of logic where it's just like, I'm this little tiny autonoma and I do what I've been told, and when I encounter SET, I just emit a set token and I move on, and I do whatever. So the way this works is you start with an initial state function. Notice the state function is recursive, and it returns a pointer to another type of itself. And then we have this loop, and we say start at the initial state, lex that state, and then it'll return a new state, and we lex that new state, and we keep going until we get a nil state, and then we know we're done. Okay? And that way we can create this, basically a call stack of lex states, except it's not a stack. It's just transitive states, where you go from one state to the next, and then you've lost all memory of your previous states. And then you just go to the next, and you go to the next. And it makes it really easy to just flow through. Okay? So before we can actually write one of those state functions, we need to be able to send tokens back. Okay? So the Lexer it's been given, if we go back, slow down, oops, too far. If we go back here, the input to the Lexer was a string, right? Our text files are not going to be megabytes of code, right? They're going to be small, keep them in RAM, simplifies the logic. You could use an IO.reader, not too hard, but let's just keep it simple. We're just going to use a string. Okay? So back here, the emit function, what we do is it takes in a token type, meaning, hey, we just found a token of a certain type. Let's emit it onto the tokens channel. So the Lexer has this channel, and it emits the token onto that channel. And the way it gets the current token is it just has two pointers in the file that it's been moving around. And it's got the start position and the end position. And as you read room by room, your end position is moving, and your start position is staying the same. And then you say, emit, I found a token. And so you take that entire string between those two pointers, and you put it in a token as the value, and then you send that on the channel. So that's what the current function is doing, is it's getting you that substring from the input. And then you just move your start pointer to where your end pointer was, and then you go from there. Okay? So really simple. Pointers in the file, moving them around, and emitting tokens. So, back to an example Lexing state function. Okay? So, in our language, if we encounter a number, it can be one of three things. It can be a number. So, let me rephrase that. If we encounter a single digit, if we encounter the next rune is ASCII 0 through 9, then we know that we are either going to be seeing numbers, a duration, or a time. And so, well, we write a simple lexer that handles that. And I removed all the cases from the top function for number and duration, just to keep it short. But here's the case for time. If we find a colon, then we know we've found a time. So what we do is we read all the digits, and then we find a colon, and we say, oh, we're definitely reading a time now. And so you just return the lex time digits state function, right? So now we just pop down into this lex time digit function. Okay, so what this does is we've read a colon already. So now we just for loop reading L.next, which is give me the next rune. And if it's a digit, we keep just reading, moving our end pointer. But as soon as we get to something that's no longer a digit, no matter what it is, we say back up the pointer 1, because we read too far, and then emit a time token. Because, hey, we just found a time. And then we ignore all space after that token. And what ignore space does is it just reads while it has white space and moves the start pointer past it. And then we return lex AMPM. What does lex AMPM do? It expects the letters AM or PM, because a time is going to have an AM or PM. That's what we decided anyways for our language. And so, and then that lex AMPM, once it's finished, well, there's no context for what should come next, so it just returns a top-level state. It says, okay, we're back at the normal global lex token function. And then that one goes and it does the next thing. Right? So we went from top-level function to number or time or duration to time digits to AM/PM to, okay, back to the top, right? But we didn't have to pop a stack or anything weird like that. We just, all the state is encapsulated in simply which function we're in. And we can just move forward. Okay, so then the cool thing about this is it lets you control the behavior of the language really easily. So which version of time syntax should we use? Should we require that there be no space between the numbers and the AM/PM of the time, or should we allow there to be spaces, right? And, well, you've got this single line here that says ignore space. If we just remove that line, then you've now required that an AM/PM token always follow right after the time token. And, or you don't mind having space there, you leave space in, right? And you get control over how you want your language to look and over the choices that your users get to make, right? So it's probably more natural to put a space there. So I decided to, just have spaces there. It has the disadvantage where you could put like all kinds of spaces, right? You like new lines and who knows what, and like put the AM way down here. But reasonable person's not going to be doing that intentionally. May do it accidentally. But you can auto-format DSLs. Not that hard. So we'll come back to that later. So, okay, so we're done with lexing. We've gone through an example of what it's like to lex, and we've got this list of tokens coming back, right? Okay, so parsing. We need to consume this series of tokens, and we need to produce an AST. But before we can produce an AST, we need to define what our AST looks like. And to define an AST, we need to have a grammar for a language. So when you start talking about grammar, people are like, oh. I am anyways. I'm like, I didn't like English in school. I don't want a grammar. But this is really simple. There's lots of different ways you can define a grammar for a language. This particular syntax is called EBNF, Extended Bach-Knowles Normal Form. I don't know how to pronounce his name. I'm sorry, whoever you are. But
I'm sending him the recording after this.
Okay. Great. Thanks, Paul. Okay, so the way this syntax works is really simple. On the left are called production rules. On the right is what they turn into. And you can replace anything on the left with what's on the right and vice versa, and it's just fine, right? So a program, and the curly brackets mean repeated. The pipe character means or, kind of like regex. And the single parentheses is just once. So if you look at time, it's digit, colon, digit. Well, those should be curly brackets. Fine. Oops. Those should be curly brackets for repeated multiple times. Anyways, I'll fix that later. And then AM and PM, you You can have one or the other, but only just one. And then a dot means that's the end of that production rule. Okay, so we need a grammar. This grammar, though, is going to be, and if you kind of look at it, there's like, you can see the keywords in there, you can see how things relate. This grammar is going to basically dictate exactly how we write our AST and our parser. Okay, so let's look at the set statement production rule from that grammar. So we say, when you have a set statement, you expect the literal word set, aka a keyword, and then you expect something called a path match, and then you expect a value. Okay, so when we go to write our AST, we're going to find, first we're going to find a node in our AST, and the only common function it really is going to have between other nodes is where did we find it in the file. So it's going to have its position function. But then we're going to define this concrete type set statement node, which is going to find that node in our AST. And what is a set statement? Well, it's got its position, and it's got, so this is, the context of a set statement is it's a device, right? So the generic thing is it's got a path match node, but it's going to be named device match, right? So we've got a device match node and a value node. So essentially we just took set statement and said, oh, there's a keyword literal, so we can ignore that. Then there's two other production rules. So we're going to have two other nodes in this node that reference those nodes. Right? Does that make sense? I don't know if I explained that very clearly. I'll try and say it again here. So when you're defining your AST, you look at your nodes, and you define a node for every production rule you have, and then you look at the other nodes, other production rules referenced in that production rule, and they become a field on that node with a pointer to the other node of that type. Okay? So then, when your parser is going, you're going to get to a point where you say, I expect a set statement to come next. So I'm going to parse a set statement. And we're going to return a set statement node. So we're going to say p.expect a token set, aka we're expecting a keyword set. Okay, and then we get that token back. Anybody looking at this going, where's the error handling? Okay, I'll tell you where it is in a second. Let's assume that we get a set token, and we're good. Okay, so the next thing we do is we say p.pathmatch. That's another production rule. And so we read the path match, and we get a path match node back, and we keep a pointer to it, or a reference to it. And then we say, oh, now we're expecting a value, so p.value. Right? And we get a value node back. And then we simply return our set statement node with the position, which comes from the token where we found the set keyword. And then we put the path match node and the value node. And boom, we built our AST. We built 3 nodes. Question?
This function that you're implementing is basically to implement one of the rules that I had in the previous slide, correct?
Yes, and the rules repeated here on top. So yeah, so set statements, 1, 2, 3, 4, 5, 6 down of the normal production rules, not the literals. And
but this you write what, in a piece of paper on a text file, and then what you do is afterwards you implement it on the right.
Yeah, so on the left you write a grammar on this one, and you can just put it anywhere. It's nice documentation describing what it is, but then the actual implementation is what you do over here on the right. Yeah, exactly. In fact, I haven't really talked about it, but you brought it up. There are such things as parser generators, because what we're talking about is so straightforward based off the grammar that yes, someone wrote code to write this code for you.
So you can create a definition file like before?
You can create an even file, and it'll just generate you a parser.
Wow.
Right? Yeah, so Yak is one from, I think, early 70s even that things existed. Maybe just 80s, I don't know.
Forever.
Yeah, forever. For my lifetime, so therefore it existed since I was born. Yeah. So
it's included in Go until 1.8, right?
Yeah. Since we're here, why would you use a parser generator versus write one by hand? 2 things. One, parser generators tend to have a pretty high learning curve to set them up. Writing this grammar, like I said, I already have a couple typos in this grammar that I just found looking at the slide now. So you can communicate the general idea. When you're sending it to a parser generator, you have to be explicit, right? You can't have a typo or it'll generate the wrong grammar and you'll be confused. Second is when we get to things like we want good error messages. Parser generators don't have the context of what your grammar means, and so they can't generate really good error messages for you. They also, when you get to the things like, hey, I want to auto-format my code, it's actually pretty easy if you write your own parser. Not necessarily so, these are features that are easy to add on yourself if you want them to your own parser, but in general, a parser generator is like, well, I'm focused on parser generating, not on all these other features that I may want in my parser. So those are your trade-offs. That being said, I'm currently in the process of writing another DSL for work, and we're most likely going to be using a parser generator. So there's reasons for both. The particular reason we're using the parser generator this time is because we want to be able to parse the language in multiple languages, right? So this is written in Go. If you want to parse this in JavaScript, you got to rewrite it all in JavaScript. Then you got to make sure your implementations are the same, right? If you use a parser generator, you're going to have a lot better chance of those being equal implementations. Yes, Dave?
I was going to point out how much I love that those parser generators basically use that grammar as a DSL. Being something specific.
It's
for that.
Inception.
Yeah.
Yeah,
Inception.
the recursion. So we're looking at using the PEG,
Okay.
PEG parser. And yeah, I was looking through it today. Yep, and there's a peg.peg file, and they've generated the parser with PEG. It's great. Yep. Okay. Okay, so here we look at the set one, and this one had a couple of keywords. Well, I had one keyword and 2 other production rules, but didn't have any alternation or anything like that, right? So here's the block statement. In other words, it's a statement that it can exist in a block of code. Okay, what kind of statements can exist in a block of code? Those 5 statements, right? No keywords, no other production rules, alternation, you can have one of each. So we simply peek at the next type, and then if we see that it's a set keyword, or a get keyword, or a var keyword, or an at keyword, or a when keyword, we go down that branch and we parse out that token. Or we consume those tokens to create that branch of the AST. And then we can do nice things like, hey, I got an, like the default case is, I got an unexpected token. And you can say what tokens you are expecting, and you can then send in the token that you got. So error, I found a colon when I was expecting one of these things. Okay, so then another thing here is, what does this mean? Get master bedroom /star. So obviously the DSL isn't very familiar with you yet, but the thing on the first one was like a location, a thing on the right of the path was like the kind of thing it is. So this is like, get all the things in the master bedroom. Well, that doesn't have a lot of meaning in this language, right? Like we could go get them, but we can't really assign them to a single var and reuse that value. Maybe we can make map types or something in the language and reuse those. We want to keep it simple. So when you get something, we're going to say you have to get a single value. So this doesn't make any sense as far as the language is concerned, to say get everything in this location. But you want your parser to be simple, and you want it to be able to just consume one token at a time, maybe where it peaks at the next token before it does something, but you don't want it to have to look n, or aka infinite tokens down the line. You want it to be able to look at just 1 or 2 tokens to know how far it needs to go. So since paths could be multiple paths, you get multiple separators, and technically a path could be infinitely long if someone want to write one, right? The parser would not be able to determine whether this token, whether the path that it's going to read has a wildcard in it or not, without reading the entire list of path tokens. So we're just going to say, forget it. It will be valid syntax, but it will be invalid AST. So it's okay for your parser to read something syntactically, and then generate an AST that represents that syntax, and then later when you go to evaluate that or whatever, you say, error, this wasn't actually valid, right? And that's why you want to preserve your position information all the way through your AST. So, I mean, who's written syntactically valid Go code that didn't actually have any meaning, right? Right? I mean, that happens all the time. In fact, if you use like the features of like format your code and run vet and these kinds of things on your file when you save, you really quickly learn the kinds of things that the parser picks up, and then the kinds of things that the compiler picks up, right? Because I don't compile my code every time I save, I just run it through GoFunked, which lets and parses it, right? So you really quickly kind of like, oh, that's a syntax error and that's a semantic error. Anyways, okay. So we've talked about parsing. Now on to evaluation, and we're nearing the end. So we're good here. So we now have an AST that represents the syntax of our entire tree. So we want to evaluate it. We want it to do something, right? So obviously, in the context of this, let me take a quick note here. I found something called the MQTT Smart Home, and they define a spec for exposing devices over MQTT, the message passing protocol, for your smart home. I've liked smart home stuff for so long that I have a bunch of old hodgepodgey stuff that doesn't conform to any kind of standard. And so wrapping all of that in an MQTT standard has been really simple for me, and I quite liked it. So I've actually written code for most of my devices at home to wrap them behind this nice MQTT standard. So this DSL actually calls into that standard. And so these get, set, and other operations are actually part of that standard. That's where this DSL came from. So when we're going to evaluate that, all we're really going to do is read the AST and then call functions on that interface that was defined for that MQTT Smart Home standard. Okay, so we have an eval node. We get a node from the DSL. Notice that I'm not showing you package information, but I think this is really important. The evaluator is not in the same package as the lexing and parsing and the AST. I think the lexing and parsing and AST should be the only thing in their package. And the public API for the DSL is the AST. So instead of putting a bunch of functions on the AST nodes themselves that do things like evaluate or format or anything like that, that creates a lot of problems because you end up putting a lot of logic all over the place. Instead, the public API from the lexing and parsing is just an AST. So when you want somebody to do something with your language, you pass them an AST. So the evaluator here is receiving an AST, and it's totally independent of how the language was implemented other than it knows what the AST means. So it says type switch on this thing if we get a program node. Remember the program node was just the node that represented the entire program. So it's just got a list of other statements. So we say evaluate the list of statements. Hey, if we get a set statement, go evaluate the set statement. And all that does is on the actual server that's, or the client rather, that's running, it sends an MQTT packet that sends the set packet over the MQTT protocol. And the get sends the get packet, etc. And then that's it. We just simply walk our AST recursively like this, and we execute these steps. Okay? So, time for a demo. Who's heard of REPL before? What does REPL stand for?
Evaluate something loop.
Yeah. Run, evaluate, prints, loop. Okay? So look at my code there in that loop. We've got, or rather read, sorry, not run. Read. So we read in, off standard in, single line. We send it to the parser. We get an AST. Notice the lexing step is gone. It's nice to hide the lexing step from the end user. Like the actual parse function of the DSL takes the text, calls the lexer, passes the result of the lexer into the parser. And that way, you don't make your users think about that because it's a simple abstraction. And then we evaluate it. And then we print the result. And then we loop. So that's it. That's all there is to it. So I've actually got a little demo here. I wrote a little REPL for this language. It actually works. I've got a little Raspberry Pi with me. And I didn't have like my house to bring with me so I can turn my lights on and off. So I have two LEDs on a breadboard. And we've got red and green light. And we're going to show this little DSL in action. So the only problem is the little power cord's a little short. So the Raspberry Pi might just sit on the floor. Works. And at this point, I'm going to steal the HDMI from there, toss it on the Pi. Oops. Grab the keyboard. Okay.
Do you need someone to hold it up?
Yeah, that might be nice. Just kind of. Thanks, Dave. Come on over. Okay, we're getting sweet. We're getting nice boots.
Can someone actually hit on the light? I think I. Or I guess that's true. You want to see the LEDs, but
Yeah, I can see. Okay, we'll just let it go
Okay.
here real quick. Squat down. Okay, so here we are. Look at my password. Okay, so I got two files right here. Oops. So I called this thing Jim. My home assistant's named Jim. I call him Jim. And then they actually like personify something as like Jim worked really well. So yeah, the language I created, I called it Jim. And so then, yeah. So then we've got PyDemo. So what PyDemo does
Can you
is
command plus on this, or is this?
I
not
can't
a-
make it bigger. I researched making the TTL because this is just a
It's
TTL.
TTL. It's not.
It's-
Okay.
or TTY rather, and it's actually the largest font they let you use. It's a 19-point font, so I apologize for that being a little bit small. But the PyDemo by the way, Go is awesome. Cross compilation. Wrote this all on my laptop. Cross compile, SCP, done. Awesome. So the PyDemo thing runs a little MQTT client, but it actually connects to GPIO pins, and it's the receiver of those set and get commands. So we'll just start that guy up, and then we'll go to another TTY. We started him with root privileges because I'm lazy and didn't set up privileges on the GPIO pins. Okay, so now we're just going to start Jim. Oops, / Jim. Okay, so I'm also lazy, and I didn't create a real console library here, so there's no prompt. So it's just waiting for me to read from standard in. So we're going to say get Raspberry Pi red. Okay, so it's going to tell us that is off. Okay, get Raspberry Pi. I also don't have history, so that's fine. So get Raspberry Pi green. It's also off. Okay, set. Here comes the moment of truth. Raspberry Pi red on. Boom.
Oh,
there it is.
Hey.
Okay.
Live demo.
Raspberry Pi red off. Oops. Right? What happens if I type in junk? Okay, it says unknown command. Wasn't able to read it. Okay? So then we say, I don't know, when Raspberry Pi red is off, set green. Oops. Raspberry Pi green off. Okay, so we just loaded in that when statement. There's no return from it and no immediate action. Okay, so set Raspberry Pi red on, right? So it's on again. Oh, and then we want to set Raspberry Pi green on. Here we go. Set Raspberry Pi red off. So now, since we're going to detect that red is being sent off, we're also going to send the command back to the parser, or back to the evaluator, and turn green off. We just have closures in our DSL.
Wow.
Right? That was simple. And, okay, so then this language also allowed for one more feature. When Raspberry Pi red is on, wait 5 seconds, set Raspberry Pi green on. Okay? Set Raspberry Pi red on. Then count 5 it slowly. And green's on. Cool. So that's it. That's all I implement in language. I didn't implement scenes or the add or anything like that, just the set, get, and when statements.
That deserves applause.
But
everyone watching this later is going to get sick.
Yeah.
okay. Wait for it. Okay. There's the demo. Okay, so real quick, just wrapping up. Lessons learned from. So I wrote TickScript initially 2 years ago, roughly. It was started in September of 2015. And so my lessons learned from running a DSL for a product that's being used in production as an open source project, so across all kinds of different environments, and all kinds of, some people say open source users are quite whiny. Sometimes they are, sometimes they're super awesome. Writing and maintaining a DSL has not been difficult. In fact, we have one open source contributor that contributed just-in-time compiler for TickScript. I was like, sweet, let's take it. And so, wow, it was awesome. And because TickScript is a little bit dynamic in its typing system, and so it turns out just-in-time compiler for it was really useful and helped make the evaluation of TickScript be allocation-free, which is also important for Go. Okay, so, and then, like I said at the beginning, in summary, write a DSL because you want your users to think about a problem in a certain way. In Capacitor and TickScript world, you want them to think about their stream of data and what they're going to do with their data. You don't want them to think about for loops and the index on their for loops to make sure they didn't have an off by 1 error, or about the serialization format of their data, or about where it's being stored in RAM, or about any of that, right? You just want them to be able to think about their data, how they're going to reshape it, and what they're going to do with it. And so a DSL works really well for that, because you take an entire class of problems and you eliminate them, because they can't have errors where they got an off by 1 error. They just can't have them. The code will always do those kinds of data management things for you. But you also introduce a whole class of new issues where they want to do something that they can't express in the language. So now you have a choice. Either say, no, we're not going to support that, or go fix the language and make it more rich. But then you're kind of going in the direction that you didn't want to go. Or you have a totally other option, which is what Capacitor does, which allows you to write your own code in a general purpose language, and we'll pass the data to you back. Right? So if you want to do something crazy and complex, you want to write in a general purpose language, go have fun, go do it. Right? You don't want the DSL, just write a little tiny template one that calls into your code and off you go. So that's worked out really well for us. And a lot of people complain that they have to learn a new DSL. They're typically programmers that complain because they're like, I've learned 100 languages, I don't want to learn 101, right? And I'm there too. I don't always want to learn a new language. I always want to write a new language, but no. So anyways, it's an exchange, right? You trade a whole class of simple programming errors, or not even simple ones, but really obscure errors, and you've constrained the problem to, you have to do these kinds of things, but you've now constrained what they can do, which is, sometimes a good thing when you can constrain what users can do. Okay, and then the other thing this has probably been the biggest thing that we did wrong with the tick script and the DSL. If you're going to talk to a capacitor, you have to write the DSL. All the DSL does is generate a DAG, a directed acyclic graph, of what your task is going to do, how it's going to move the data around. So we should have made that an API in and of itself. So you could just give us a DAG and we could run it. And that way you don't have to write tick script. You could write a Python library that generates your DAG, and then off you go, right? Whatever you wanted to do. In fact, like I said, we're in the process of, because the tick stack in FluxDB has two languages, has the query language and tick script, and because they grew up at separate times and whatnot. So we're working on unifying them right now. That's why we're rewriting a new DSL. So we're absolutely making that DAG that the DSL describes a public API so that you don't have to learn the language just to use the product. But using the language is a way to get started up and quick and not have to, kick your wheels trying to learn some weird framework or something. Okay, so that's pretty much it. Here's all the links I was telling you about. These slides are on GitHub. GitHub, Nathaniel C. Go Talks. You'll find the slides there. The links here are there. So my little repo of Gem, the DSL, and my other home automation things in there. And then the talk by Rob Pike that actually kind of inspired all this work. Like I said, source code, go look at that for actual text template. And then if you want to see TickScript source code, there it is as well. It's a nice little tidy package with a just-in-time compiler. And then there's the link to the smart home specification. So that's it. Thank you very much. Other questions? By the way, yeah, go ahead.
So when you talked about tag, I have a question, maybe that will answer. So I have to write the query right on their domain specific so that it will run, right? But what if, to create the tree, right?
Right.
What if I have something that already has the tree, but I want to create this?
Yes. So if you've written your own parser, you can do crazy things. So Go Fumpt. Have you guys looked at how that works? It's really simple. Go parse, AST. That's another link I should have had. The parser for Go is written in Go. You can go look at it. A lot of this, I've spent a lot of time digging around there trying to figure out how they do stuff too. You create an AST, and from that AST, you can regenerate the text. And so I'm like, well, let's do that for TickScript as well. So I actually have a Vim plugin for TickScript that both gives me syntax highlighting and will auto-form my tick scripts on safe. I just ripped off Fatih's Vim Go, took just the part that called Go Fumpt, and replaced it with Tick Fumpt, and it worked great. I've never done Vim plugins before, but it worked. and then since I did that, there's now a Sublime tick script editor. There's an Atom one. There's one for VS Code. Just the community just took those and it's hey, off I go. It was pretty sweet. So that's one of the other costs that you pay with the DSL. So you don't have great integration with an IDE, but the language should be simple enough that shouldn't matter too much, right? But so the answer is yes. In fact, it's as we're writing this new language, it's absolutely a requirement that you can go all the way up and back down the chain. So if you were to just send me over an API call, the DAG that describes the task, if you wanted, I could just send you back the query that would have, the text for the DSL that would have created that. And without you ever seeing that text, right? So you can just generate the text out of thin air. Cool. Other questions?
So is there anything built-in limitations? So like a lot of languages have keywords, and
Yep.
your variable can't use that keyword.
Yep.
Could you have a variable named set or get, or like a location bedroom set, or is that going to cause a
So
problem?
my DSL has a lot of keywords, and it is annoying, and it probably would cause problems. I haven't run into it yet in this weekend.
So if you wanted, if you wanted, like if you're getting information from your home automation system, and you already had something in there called set,
Yep. I might have
use
to.
that, you might have to implement some sort of escaping that you could have a bracket name instead of a normal name.
Yeah, or maybe I have a little bit of context where I know if I'm in a path that any word goes, right? Because I have a token for words and a token for the specific words. Maybe I throw out all my keyword words, and then when I expect a keyword word, I assert that I get a token word, and then assert that the value of that token is the keyword that I wanted. That would be a way around it. But yeah, in general, don't like keywords in languages because they take names away from your users. I didn't bother to really think that through on this DSL. In TickScript, there's 3 keywords: var, true, and false. And so everything else is free game. There's even like a lambda keyword, but it's not actually a keyword. It's just a lambda key. And then you can actually name things lambda if you want. Other questions? Yeah.
So typically you find people trying to do, I think, a little bit like this, but using YAML or using JSON, and then they do create abstract syntax trees or anything like that, and then they generate code or they generate other things. Like, how do you see the advantage of this eventually using this compared with just parsing YAML file with certain rule?
Yeah, I mean, if you're going to use a data structure to describe something, that's totally fine, right? You get a data structure, right? You could write a YAML file that represents the data structure for that abstract syntax tree and then just go evaluate it, right? I think the point, though, is you're trying to cater to an audience that may not know YAML already, right? If the set of your users is a subset of people that know YAML, then use YAML by all means, right? Use something familiar with them. But if there's a lot of people that use Capacitor that are not programmers, right? They're just BI folk that, they understand programming, they work with developers a lot, but they're mostly interested in the data, right? So a simple language that they can learn is great, and maybe they don't know YAML already, and so learning YAML versus learning this is going to read a lot better, the DSL will, because it's, again, in the correct abstractions and context of what you want them to think about, as opposed to making them think through data structures that represent transformations. And in fact, YAML is really hard to represent a DAG, right? The way you typically represent a DAG when you serialize it, because serialization structures can't be recursive. YAML can. Let's not go there. But you typically just create a set of all your nodes and then a set of all your edges. And then the edges just say this node points to this node and this points to this node. So yeah, you've communicated it to a program. When a human goes and reads it, you have to jump all around the file to figure out what it means, right? So, and in this specific context, that's why a YAML program would be really difficult to use or to push on a user. Right? At that point, it's like that would be, in my opinion, the worst of all the worlds, right? General purpose language versus DSL versus configuration, like that kind of, yeah.
Also, another advantage, I think, is trying to figure out how to word this. Okay, so if you want to tell someone about a bug in your code or whatever, if you're telling the guy next to you at work, you use a very specific set of vocabulary, and concepts are abstracted away into words, right? Whereas if you want to explain a bug to like your wife, and if your wife's not an engineer or something else, you don't have that common base of vocabulary and concepts and things to build on. And so it's very verbose, and she probably gets bored and stops paying attention. She probably does anyway. But, but like with DSL, for example, you can basically define high-level concepts or vocabulary very simply for your end users. You can say things like set instead of like turn that light switch on and do this thing, whatever. It's just like set means this, and you're good. I don't know.
Yeah, so back to the TickScript example. Mean isn't a hard thing to implement, right? You have to loop over all your code. It's not too far, and then you have to sum it and count it and then divide it and get your answer, right? What if you had it on, accidentally double counted something, right? You don't even have to think about that here. It's just I want the mean, right? So mean simple. What if you want the whole winter's forecast, right? Okay, whole winter's requires running an optimization algorithm. and Neldermead and all this stuff. And it's like, well, I don't want to think about that. But mean and whole winters are the same level of difficulty in this language because they're just pipe mean, pipe whole winters, right? You want to call out to your highly tuned machine learning model, it's just pipe name of machine learning model, right? And it's just really easy to, like Dave's saying, you create this vocabulary for these higher level concepts about things that you actually care about, not about the minutia of how it gets done.
I got another one on that front where you're starting to do an integration that is going with other systems or even other languages, right? So how do you implement something that says, okay, I'm going to maybe run some arbitrary bash script that you want inlined in your language? How would you, having designed a couple languages, how would you do that kind of escaping? Because I mean, so like XML had C data, like you put whatever you want in a C data section. And then some people have triple quote, or some people like, how have you found writing a DSL knowing that you can no longer have your arbitrary rules on a chunk inside of something and you want to be able to escape into another language or another DSL?
Right. So if you feel like your users are commonly going to need to break out of the DSL and do something really complex, that's a really good use case for an internal DSL because they have the entire feature set of the general purpose language at their fingertips, but they're just not using it most of the time. But then when they need to break out and use it, they can. If you're going to write an external DSL, that's really not an option. And in fact, if you don't want it to be an option, use an external DSL, right? So we very explicitly did not want that to be an option in TickScript because we provided another way for them to go break out and do their custom logic via the called UDF, user-defined function. We just call out to a socket, send you a bunch of data, and you send it back. And that's been performant enough, and we do that. So to reiterate, an external DSL, you probably just can't do that.
So,
right.
So have some sort of escape hatch and
Yeah.
say you're now outside the scope of this DSL. And
You
gotta-
could, but I think at that point, I mean, this personal, my experience here would be, I wouldn't do that.
Yeah.
If I felt like that was a need, I'd use an internal DSL, like I said. So like, for example, other things in the space of capacitor, something like Apache Spark. They've written everything in Scala initially, and so what you do is Scala is also a language that you can really manipulate, and so they wrote internal DSLs for Scala, meaning that here's the subset of Scala that you use to write normal DAGs for Spark, but then when you need to break out and do something crazy, go write Java code if you want, and then link it into the Scala code, or just go write your own Scala closure, and we'll ship it all around and everything. So they do that. In fact, and they also now have like Python bindings and C bindings and all that kind of stuff. And those bindings work because they have that DAG representation of the intermediary layer.
So like almost an interop level of you know.
Yep. Well, sweet. Thank you. I'm willing to chat with anyone in person if you didn't want to like ask questions. And like I said, we're hiring at Influx. And so if you want to talk to me about Influx or more about what we do there, just let me know.